Okay, somehow I can't share the screen. So I think somebody has to give me power to, to share the screen.
No, I think just previous speaker needs to stop sharing.
Yes.
Okay.
I can do that, I think.
Okay.
Can you try it now?
Yes.
Sorry.
No, it works. Yeah. Okay. Wait a second. Okay. Good afternoon, everyone. I will try to be brief so that we can all go for lunch. So I'm going to talk about cosmological detectors of ultra-high frequency gravitational waves. And essentially, I will focus on the Gerstenstein effect, which has been widely discussed in this workshop. And as you all know, essentially the idea is that we focus on the conversion of gravitational waves into electromagnetic waves. Okay, so I will, before discussing the cosmological aspects, I will briefly introduce and motivate why we are interested in cosmological detectors. So, okay, the first thing that I want to emphasize is that this is a classical process in the sense that it only involves classical electrodynamics in general relativity. And the rate for the conversion is not proportional, sorry, is independent of the Planck constant. And as such, this process is strictly analogous to axion photon conversion. And because of that, many bounds or ideas that have been studied for axions can be adapted to gravitational waves. We have seen this already in the workshop. For instance, the talk yesterday on detection of gravitational waves using these axion experiments is summarized here. Okay, the problem is that involving gravity, the conversion probabilities in all these terrestrial experiments are extremely small. And the idea of using astronomical or cosmological detectors is to compensate this by using something that has a very large size. And what is the largest thing we can consider is the CMB, right? So the entire universe, and in particular, the distances of the CMB. So actually, what I will discuss is based on a work that I finished with Valerie last year. And this work has to do with the distortions of the CMB due to the Gerstenstein effect. Okay, we were not the first people to consider this. And in fact, there is a list, and I think the one that I'm showing here is actually not complete. But there is something that is new in our work, and it's the fact that we took into account all the new developments that have been happening in the last decade concerning cosmic magnetic fields and multi-messenger astronomy. So that's what I will talk about now. Okay, so of course, for using the Gerstenstein effect, we need to discuss magnetic fields. And in a cosmological context, we need to talk about cosmic magnetic fields. And they are parameterized by these correlation functions. And essentially, these things allow us to introduce two things, which is all I need to study the Gerstenstein effect on cosmological scales. So one thing is the average magnetic field, which can be just calculated from this primordial spectrum of the magnetic field. And the other thing is the coherence length. Okay, so this field of cosmic magnetic field is very broad, and there are many details, many different perspectives on this. So if you are very interested in this, and also to follow the theoretical details of our paper, I invite you to have a look at this review from 2013 from Durer and Neronov, where all these things are discussed in a lot of detail. So, okay, but the bottom line of this is that we are interested in two magnitudes, which we can, of course, put in a plane. One of them is the magnetic field, so the average magnetic field, and the other one is this coherence length, okay? And now, so what is new, or was new back last year when we finished the paper? So the first thing is that we now have an upper limit of the order of 47 picogauss on this plane. So, okay, so we have to consider the Gegenstein effect under the assumption that large magnetic fields, I mean, that magnetic fields do not exist this bound. Okay, and what is more interesting, and I think this is really, I think one of the most interesting parts of this, is that there are indications or evidence that there is actually a lower limit on this plane. And this comes from blazars. So I will describe these things in a second. But for now, I just want to say, I want to emphasize that this is really a great motivation to consider the Gegenstein effect. Because of course, if this is really a lower bound, that means that we should have a signal. And okay, this is what we aim to calculate. Okay, so I will discuss a bit these TB blazars and how they indicate that there is a non-vanishing cosmic magnetic field. So these are very distant objects, actually, of redshift of order 1 or below, that are producing gamma rays. Okay, so here I have a small cartoon of the situation. So we have this laser that is producing gamma rays, and then these gamma rays arrive to us and are detected on Earth, for instance, at HESS or Fermi telescope or future CTA, whatever. The interesting thing is that the universe is not really transparent to gamma rays. So some of these gamma rays are actually undergoing another path. So let's recall that the universe is not empty and is full of actually radiation. So we have the CMB, we have infrared light. So we have these low energy photons that are around. And if you have a very energetic gamma ray, like one of these coming from the blazars, they can meet, and then the energies are such that you can pair produce. Okay. Now this production of E plus E minus pairs will undergo further decays, so cascade decays. So it would produce more radiation. Okay. So for instance, via inverse Compton, as it is indicated here in this cartoon. So then we can, so together with the gamma ray, we should be able to observe a low energy part. Okay. And okay, astronomers are somewhat confident that they can, given the spectrum from, so the original spectrum, the primary spectrum from gamma rays from the TB blazar, they can infer what the secondary spectrum is. Okay, and this is what is shown on the right. So the primary spectrum is indicated as a dashed line. And okay, this is not what we observe, because as I said, the gamma rays are absorbed. Some of them arrive to for instance, HESS, the detector, and this is indicated with these points on the plot. But some of them are, undergo pair production. Okay, and they produce, if all this picture is correct, they should produce the black solid line that is shown there. The thing is that because of the progress of multi-messenger astronomy, now we can constrain these at different frequencies, at different energies, and then so now we have a problem, because Fermi, who is trying to observe these secondary photons, does not see anything. So then you can put a bound. So there is a contradiction. There is a problem here. As far as I understand, this is very hard to explain. So this issue is very hard to explain if you don't invoke cosmic magnetic fields. So actually, cosmic magnetic fields are the simplest explanation of this phenomenon. Why? Because you can simply assume that some magnetic field, intergalactic magnetic field, is deflecting the electrons that are produced in this gamma-gamma collision. And so then we don't see the cascade. Okay. In fact, people have, because this is so important for gamma ray astronomy, people have studied what is the effect of different magnetic fields on the cascade. Okay, and this is what is shown here on the left. So you can see the different curves. They correspond to different magnetic fields. So the larger the magnetic field, the smaller the secondary spectrum, so the smaller the cascade spectrum. So you can see that, for instance, in green, which corresponds to 10 to the minus 18 Gauss, I think. And then you can just decrease the magnetic field, and then you see that you generate, well, the spectrum. Okay, so people have put all this together in the last decade, and they concluded that there is a strong evidence from blazars of the existence of these primordial magnetic fields. And in fact, due to the progress that is expected in this field in the following decade, maybe in this plane that we observe here, we will be able to find an actual signal and not just a lower bound. So I think this is interesting. Okay, so what we are to study the Gerstenstein effect, what we are going to do is to put conversion probabilities on this plane. So this is here, and I will explain in a second. So these are the different contours of conversion probabilities. I will explain in a second how that works. Okay, so we focus in to calculate these conversion probabilities. We focus in the dark ages. So this is the era in between the formation of the CMB and reionization. And the reason for this is because during this time, the electron fraction, the number of electrons that are around is very low. Okay. Now, if you study the equations that describe the Gerstenstein effect, you see that on the one hand, you have the wave equation for the gravitational waves sourced by the electromagnetic field. And on the other hand, you have the same thing, but for the electromagnetic field. And in this case, you have to put a mass term, which is associated to this plasma frequency that is induced by the electrons. Okay, so essentially, this is very similar to, for instance, neutrino oscillation. So you just have a conversion probability of one onto the other, and this conversion probability is determined by the plasma frequency. Okay, so if you put actual numbers for what we know about the plasma frequency, so these things are known, right? So we know what is the density of electrons in the intergalactic medium, or so the density of electrons during the dark ages. And you more or less conclude that the oscillation frequency is of the order of, it's much smaller than parsec scales. So if you look at this plane here, you see that's much smaller than the coherence length that you can put in this plane. So that means that even though the cosmic magnetic fields are not expected to be perfectly homogeneous, we expect coherent oscillations to take place in highly homogeneous patches. Okay, so in that under that consideration, then the oscillation rate between gravitational waves and photons is determined by this formula that I'm writing on the screen. Now there are some subtleties on this, so I invite you to have a look at the paper where we derive all this, and we try to be as conservative as possible. The thing is that to calculate actual bounds, or to calculate the actual effect, we just have to integrate this rate along the line of sight. Okay, and this is what is done here at the bottom, and actually what is shown on the plot that I was showing before. So the color contours are just contours of the conversion probabilities. And yeah, so this depends on what we assume for the initial redshift where the conversion start taking place. Okay, we just did this. Of course, at some point we will be interested in going to very early times, in which case the initial redshift has to be the time when the CMB is formed, because that's the moment when the universe becomes transparent, and then we can use this formalism during the dark ages. And we stop at 20 because at that point the universe reionizes, and then the oscillations are essentially gone. So this effect is essentially disappear. Okay, yeah. So this small inset on the plane that I'm showing just is just a function, and I mean the conversion probability is proportional to this function. So you really here can see that the effect disappears once you go to low redshifts, so beyond reionization. Okay, so that's the conversion probability. Okay, so now let me talk about so the conversion probability as a function of what we know about the magnetic field and the coherence length. So now let me talk about CMB observations. And here there is also important progress in the last few years. So on the one hand, we know that the CMB is described by a black body spectrum with a high accuracy. In fact, even in the 90s, in the early 90s, the FIRAS mission, this FIRAS, which was part of the COBE mission, was able to determine deviations from a black body spectrum, and they are very, very small. So I mean, you don't see them on the plot, right? It really looks like the Planck formula. Yeah, exactly. So what our idea was, okay, so we have this. Let's suppose that we have a source of gravitational waves in the early universe, and then that we have this conversion into gravitational waves due to the cosmic magnetic fields, and that somehow one of these photons produced in the conversion process distorts the CMB, right? It's a very simple idea. And yeah, so if I invite you to have a look at the paper where we work out the details. I mean, you find that the distortion of the black body spectrum is just proportional to this conversion probability that I was showing before. That's actually the reason why we were interested in that P. Good. So the thing is that, and by the way, this formula applies only in the Rayleigh-Jeans scale, which is the most important and the most interesting frequency range for these studies, because it is in this range where we can say when we can beat eventually, or in the long-term future, this ineffective constraint that has been discussed for a long time during the workshop. Okay, so in this Rayleigh-Jeans scale, the most, as of today, the most important constraint is given by RK2, which was a mission from last decade that measured the CMB spectrum in this part, and it found really a spectacular agreement with the Planck black body formula. So then we can just, since the effect is proportional to this P, we can just put a constraint on the gravitational, the characteristic strain of the gravitational waves as a function of the frequency. And this is what is done here. So, okay, so let me explain a bit here what's going on. So on the left, I just explained at the beginning, I'm showing the conversion probability as a function of what we know about the cosmic magnetic fields. And these colors corresponds to some point in that plane. So now if I go to the right, so since we don't know exactly what the magnetic field is, I just have to associate to each color one constraint. So this is the problem with astrophysical constraints, right? So we unfortunately have uncertainties that are very large. So, okay, and then if we use this arcade measurement, we can put this this bound. Okay, now for comparison, I show the ineffective bound, assuming a broad spectrum, so almost a scaling variant over 1 decade or something like that, and then a spiky spectrum, because the ineffective bound depends on what sort of a spectrum you have. So if you have something like a line, you really have a weaker bound. Okay, and then for comparison, I'm showing here laboratory experiments. And I think this is the reason why this is, well, for me, the reason why this is interesting. So if we are lucky and the cosmic magnetic field is close to this CMB bound, so, and if we have coherence lengths of the order of kiloparsec, as is shown here, then we will have a very strong bound. If the cosmic magnetic field is very weak and is close to this laser lower bound, and or if the coherence length is very long, then the bound is weak. Nevertheless, it is still stronger than, for instance, these detectors that use magnons. Good. So that's one thing. And the thing is, as I said before, there are a lot of interesting and a lot of expected interesting developments in the near future in the religion still of the CMB spectrum. For instance,
there's 5 minutes.
Yeah, I will conclude very soon. So, for instance, there was this experiment by Edges, which tried to detect this. I mean, to study the end of the Dark Ages. Let's put it like that. Okay, so it is a very simple experiment. You can see it in the picture, and they found something very puzzling, and it's that there was this absorption feature. Okay, and this exactly happens that in the Rayleigh Jeans still of the spectrum, right? So we can convert then this. I mean, if we assume just that this discrepancy that they found is just astrophysical, and we just use their measurement as some sort of upper bound, then we can also put a bound on the gravitational wave signals that are centered around that particular frequency they measure, and that's what's shown here. And as before, if the cosmic magnetic fields are sufficiently large, then this constraint is very good. It supersedes terrestrial experiments, and if not, then, well, it depends, no? So yes, I will conclude now, because I think we all want to go for lunch. So the Gegenstein effect during the Dark Ages provides a powerful way to probe gravitational waves in the megahertz and gigahertz range from distortions of the religion's CMB tail. And with upcoming advances in 21 centimeter astronomy targeting precisely this frequency range with increasing accuracy, it becomes conceivable to push the limits derived from radio telescopes below the cosmological bound, constraining the total energy in gravitational waves. And yeah, that's all. Thank you very much. I can take questions.
Thank you, Camilo. There's a question by Andreas.
Hi, Andreas.
Thank you very much, Camilo, for the nice presentation. Question is, so what are the prospects to pin down pin down or to make the white region in your magnetic field versus coherent lengths to make it smaller and smaller, so to say, because otherwise you will always have this a huge range in possible bounds, so to say, if this doesn't get smaller. So how this can be made smaller? What kind of observations can?
Yeah, so you can still see my screen, right?
Let me see. I see myself. No, I don't see your screen.
Really?
Do others see the screen?
No.
Okay.
Oh.
Now
it's there. Okay.
Yes.
Yeah, thanks.
Yes. So yeah, this is a very good question.
The CMB cannot be improved, probably only from below. You cannot go up, or what is it?
Yeah. So I think the biggest the biggest hope, I guess, has to do with these Cherenkov telescopes, right?
Okay.
So CTA, for sure, will be able to say something. And in fact, if you have a look at the science book, you find this statement that I put there in yellow. So essentially, they say that if they are lucky, they will be able to measure magnetic fields from of the order of 10 to the minus 16 to 10 to the minus 12.
Ah, okay.
So CTA, it's
So, but
Of course,
they
this
didn't
depends
plot-
on what they observe, no? But
But
so they
didn't
have the
make-
potential to
yeah.
do this.
So are there projection plots like this for future experiments? They are not. They are
Unfortunately,
not doing
not.
this. That's.
They're not doing
that's
this.
a pity. Okay.
Yeah.
Thanks.
So here there are many things that could be done. I have the impression. I mean, of course, I'm not a gamma ray astronomer. That's probably very hard. But yeah, so what I can say is that with CT8, this thing will probably shrink. Hopefully,
But it's a good idea that you mentioned this, because I mean so DAISY is involved in this kind of study. So maybe we could point them to the way that we can learn something about ultra high frequency gravitational waves from such a improvement and so on yeah. Okay, thanks.
Yeah.
There's a question by Axel.
Yep.
Yeah, thank you. I would like to know if you see a distortion from the CMB, is there a specific pattern that you can really narrow on the origin that's really gravitational wave and not something else? So
I don't think so. Well, for instance, it could also be an axion and it will be the same, right?
mhm.
So I don't think I guess it depends on the sort of gravitational signal you have, but I don't think you can just tell a gravitational wave signal from something else causing a distortion.
Okay, thanks.
Yeah.
Yeah, I fear. Mhm.
Is there any other questions?
I have one more, if I may.
Yeah, sure.
So there you said, of course, I mean, you concentrated then at the end for the prospects on the 21 centimeters, but of course I'm more interested in the 10 gigahertz range, so to say, because of
Yes.
the cosmic gravitational microwave background. And so there you showed this arcade. Is there anything more which will come in this range, or is this or is there no
I actually
nothing planned?
Yeah, so we try to focus on the relay gauge tail because this is where an effective can be super small. I think yeah, well, I've heard different talks, people saying that this is not something impossible. This can be improved a lot, but for this you need to, of course, send a mission to space, and I think this is
So, yeah, okay.
well,
So this
I don't know.
arcade, so I didn't know this before. So there is no successor of arcade, so to say.
As far as I know, no.
Okay.
But well, I'm not sure.
Yeah. Thanks.
Okay.
Well, thanks very much to all the speakers. Those were really interesting talks, and also the questions. And we see each other in half an hour, right, Francesco?
Yes. Many thanks also to Yvette for sharing this session, and we reconvene in half an hour for the discussion session led by Andreas.
Okay. See you.
Thank you.
Bye.